Our goal today is to finish average value of a function, in particular the mean value function stuff. And before we get there, I want to show you a little trick that you can use to speed up some simple integrations. We know how to do e to the x, and we know how to do cosine x and sine x, and even a multiple of e to the x's and cosine x's. But we can actually do the integrals of not just x, but 5x, or negative 2x, or even a quarter x. And it's called the linear shortcut method. So I'm going to show you the first few answers. If you want to integrate, find the antiderivative of e to the 5x. It's e to the 5x times 1/5. Now you could do that by a u sub. Could you do u equals 5x? And trust me, that's the answer. Now, if you do this one, you get e to the negative 2x times negative 1/2. And if you do the cosine of 3x, its integral is the sine of 3x with an extra 1/3. Can you see any pattern here that you might be able to use to speed up integrating e to the 2x and 5x without having to do a little u sub all the time? Right. Now, if you see that pattern, you should be able to tell me then, what is the integral of the sine of 2x then?
Negative 1/2 times cosine 2x.
Agreed. Do you want to maybe explain that to some of the people who are still looking and can't see it? How did you figure that out?
Well, I know that the antiderivative of sine is negative cosine, and then all the pattern before was just take the coefficient and put a 1 over it and multiply it.
Sounds good to me. So if we add a little extra, like a 5 there, won't the answer be 5e to the 3x, then divide by the 3, and you're done? Okay. It's still true if the fractional part of the x, right, isn't a nice number like 3x or 2x. It will work when it's a quarter, 3/4, or a half. You just have to be a little bit more careful. If you integrate 2 cosines, you get 2 sines, right? Now, what do you think that 1/4 is going to do to the answer? How are we going to incorporate the quarter, right? When I had the 3 went there. When I had the 2 went there, right? 3, 3, 2, 2, 5, 5. What's that quarter going to do?
It's basically just going to multiply by 4.
Okay, so what you end up with is, I guess technically speaking, isn't it that? But most people would see that as a 4, which you should. And you've now got that. Now, it might not save you a lot of time, but couldn't that save you a couple of minutes rather than having to do a u sub? And it's totally acceptable for you to do that in tests and in homework, if you like it. If you find you're not comfortable with it, well, just do it the old-fashioned way, right? Just do a u sub, u equals 5x, u equals 1/4 x, and you'll still get the answer. So let's return to average value of a function, which is this guy. Here's the first question I'm going to do, number 11. 6 sine x, take away 3 sine 2x. It's going to be in the range 0 to pi, and we're going to find its average value. So let's do that first. The average value is going to be 1 over b minus a, the integral from a to b of the function and the reason that I kind of did this introduction is, isn't it a lot easier to do this one now that you've got a shortcut? So you get 1 over pi. We're going to evaluate it from 0 to pi. If you integrate 6 sine x, you get negative 6 cosine x. If you integrate negative 3 sine 2x, okay, -3 sine 2x. Won't you get +3 cosine 2x? And if you differentiate a sine, you get a negative cosine. So -3 gets you +3. And what's that 2x going to do to finish the answer off? How's that 2 going to get incorporated?
You would just divide the whole thing by 2.
There you go. You see how quick it was to integrate it because there's a shortcut. So now we're going to, I'll have to move over a little bit. We're going to put the numbers in and see what we get. We get -6 the cosine of pi plus 3/2 the cosine of 2 pi. That's the first one. Take away -6 the cosine of 0 plus 3/2 the cosine of 2 zeros. It's still 0. Okay, the cosine of pi. Well, cosine of 0, cosine is -1, so that's 6. Cosine of 2 pi is like cosine of 0, so that's 3/2. That guy is 1, so that's -6, and that guy is still 1, so that's plus 3/2. And what do we get? 6, add 3/2, take away is add, take away 3/2, and we get a very nice answer. The average value of this function is 12 over 1 pi, 12 pi, 12 over pi. We okay with that question? Always be on the lookout for me making, arithmetic mistakes, but it looks good, doesn't it? Now, part B. We're going to use what's called the mean value theorem. We're going to find C. That's a special number that has to be in the range 0 to pi, and there might be more than one. That has the property that the value of the function at this point, C, is the same as the average. So to do question B, we are essentially going to be solving when is the function equal to its average value. Would you agree that you're not going to solve that algebraically, right? There isn't really a reasonable way. So we're going to get the answer, and it's going to be done by Desmos, and it's going to be, let's say, 3 decimal places. So I'm now going to go to Desmos and set up this question. You do not know how lucky you are. Oops. When I, a long time ago, was doing calculus, which would be 50 years ago, we didn't have computers. And we certainly didn't have Desmos. Well, there were computers, but they were like, they filled up an entire room, right? And they had valves in them, right? So nobody afforded those. So we had to do all this by hand. So aren't you lucky? You now got a nice little program. I'm running on here because I can't find Desmos. So give me a second to find where it's gone. There we go. Right, looks like I should be able to switch over now because I've got a picture of Desmos. Here it is. And in here, I'm going to do y equals the sine of x. I think I need a bracket, don't I? Yeah, that's how it does it. Take away 3 sine of 2x. Looks good. And then we're going to put y equals, type in pi for pi. Question.
Was it 6 sine x for that first term, or did I miss something?
It was 6 sine x, and thank you for picking that up because I missed it. Yeah. Right, now I may have to, oops, I ripped out the S of sine. Okay, now we're only interested in 0 to pi. There's 0, I'm pretty sure pi is about there, so yes. Okay, so a little bit more, go. Can you see that the blue line, which is the average value, crosses the function at two locations? So there's actually two answers. The first one is 1.238. And the other answer is 2.808. Well, at least to 3 decimal places. Are you comfortable about how you can use Desmos to find out where the average value crosses the function? And when we now return back to the whiteboard, you'll see it's not a big deal, but have you noticed that sometimes WebAssign asks for a comma separated list? You ever remember that phrase? That's all it means. First guy, comma, second guy. That's all you do, you put in the box. Now, there are actually lots of other places, but aren't they outside the range 0 to pi? So you only write the ones that are. Sometimes there's 3, sometimes there's 2, but isn't there always guaranteed to be 1? Because that's what the mean value theorem states. It says, look, you're guaranteed 1. No way of avoiding it, but you might get 2 or 3. I think that went pretty good. We feel comfortable with that question. Find average value, essentially find C, and then off you go and do the rest. Well, actually, that's the average value. This is C. Okay, let's do another one. We'll get this finished today and get started on the next thing. Okay, where are you hiding? Here we go. There we go. Next part. Oh, draw a sketch of the situation. Part C, I almost forgot it. If you remember what our Desmos picture roughly looked like, it looked like that. And we had over here pi, 12 over pi. And it looked something like that, right? You will be given, like, I think it's 4 pictures to pick from. And your picture will look a bit funny. It'll look like this. So there is going to be the 0 and the pi. And the top rectangle, right, that's going to be the average value. So you pick a picture that has the straight line at the right place and then a little rectangle shaded. Me personally, if I was drawing that picture, wouldn't it make more sense to just draw a picture like that? But they want a rectangle, so they get what they want. Okay, now we can move on. Not really much to do here. Let's do, for my second last one, let's do a different question. This one is unique. We've got a nice function. And it's defined from 0 to b. And we're being asked to find the value of b. There might be more than 1. Such that the average value of this function in that interval is 6. So we're not even going to find the average value, which is what we typically do. We're going to find out what this number b has to be to make it that average value. So I'm setting up my general formula. The average value is integral from a to b of our function. Now I know that's 6 because they told me. And I know a is 0 and b goes there. It's 1, oops, I forgot my 1 over b minus a. So won't that be 1 over b take away 0 of 5 plus 8x take away 6x squared. And 1 over b minus 0 becomes 1 over b. And this guy becomes 5x, and this guy becomes 4x squared. And this guy becomes 2x cubed. And it's going to be evaluated at 0 and at B. So it's going to be 5b plus 4b squared, take away 2b cubed, minus a whole load of nothings. And if you distribute that, you get 5 plus 4b, take away 2b squared. And we could certainly plug this into Desmos, couldn't we? And we could find out what the solution was as a decimal. But they want us to get the value or values of b as the exact values. So that's our puzzle. How do we find the exact value to the solution of this quadratic? Whoa, this is, yeah, Math 94 stroke Math 99. Do you remember how to solve quadratic equations that do not factor? Which I believe this one doesn't. They do
formula.
Yeah. Did you think you'd seen the last quadratic formula when you got to calc? That's stuff you did a way back in the day, but no, this guy is quadratic formula. I'm going to do a little bit of cosmetics to it. I'm going to add 2b squared to both sides. I'm going to subtract 4b from both sides, and I'm going to subtract 5 from both sides. So I've now turned it into that quadratic. Does it look a little bit more like a quadratic equation should look now? And just to remind you, because it's been a while, a is 2, b is -4, and c is -1. And the quadratic formula is a pretty ugly guy. I'll tell you what, anybody want to volunteer for it? I know it's a while. Quadratic formula. Anybody want to start it for me?
Plus or minus b
No, but
or
close.
negative b. Oh,
Negative b.
plus or minus square root. B squared minus 4ac.
All over.
2a.
Very good. Agreed. Right. Now, in this case, then, I know I'm calling it x, but you know it's a bit awkward to call it b because there's a b in the formula, so I'll call it x. And what do we have? We have the negative of this guy is 4, plus or minus the square root of this guy squared, which is 16. Take away 4 times 2 times -1, all over 4, 2 times 2. So it's going to be 4 plus or minus, that's 8, square root of 24 over 4. It's good, right? It's good. Can we make it better? Any suggestions about simplifying this? Okay, any suggestions about simplifying the square root of 24?
Can't you take a 4 out of it and then it's 4 square root of 2 square root of 6?
Okay, and if I wanted to, couldn't I make it 1 plus or minus a half root 6? Agreed. And so it looks like we are going to have 2 answers. As long as both of those are positive, I can do it. I probably should check that one because it might be negative. So 1 take away 0.5 times square root of 6 is negative. So in my case, I can't use that one, and I've only got one answer. Apart from arithmetic mistakes, are we cool about the process? Now, moving on to our last and final question, and then we can start a new chapter. Chapter 7. And the last one is to do with a town where, this is question 13, and in this town, the temperature at time t is given by 50 plus 11 times the sine of pi upon 12t, and t goes from 0 to 12. And we are being asked to find the average value of this guy. So it's going to be 1 over b minus a, the integral from a to b of this function dt. It's going to be equal to 12 take away nothing, the integral from 0 to 12 of 50 plus 11 times the sine of pi over 12t dt. Okay, integrate. 50 is easy. It's just a number, so you integrate it, you get 50t. That guy is going to be a pain in the butt to integrate, but let's have a shot at it. There's an 11 there, and there's a sine. So if it was just 11 sine t, it would be negative 11 cosine t, right? But it's not t. It's pi upon 12t. Agreed? Now, haven't we done a shortcut for that? What is going to be the effect of that pi upon 12 here? Is it going to be pi upon 12, or is it going to be 12 over pi? What's going to happen to it when it comes over here?
It's going to be 12 over pi.
So just to make things nicer, it'd be 11 times 12, I think that's 132 over pi, cosine pi over 12t, t equals 0 to t equals 12. Are we comfortable with that? Right, so to get the average, I'm going to plug 12 in. So it's 50 times 12. Seen worse. Plug it in here, negative 132 over pi. The cosine of pi over 12 times 12 is just a cosine of pi. Oh, that's quite nice looking. Take away, put in 0, that goes away. Put in 0 here, and you get negative 132 over pi times the cosine of 0. Right, 50 times this guy, it's 600. What's the cosine of pi? What's the number for the cosine of pi?
-1.
Okay, so 2 negatives make it a plus. Take away nothing, doesn't matter. Add, well, let's check it. That's 1. So add 132 over pi. And so our answer becomes 1/12, 600 plus 264 over pi. If I distribute the 1/12, I get a 50. I hope 264 works with 12, otherwise that was a pointless thing for me to do, and it does. Are we cool with that guy? Now, of course, you know, bear in mind I can't count, but the process is right. So, time for a new section then. Oh, too quick. Is there anything about average value functions that you want me to go over before I move on? Are we okay? So let's move on. Our new guy is chapter 7. In particular, 7.1. And it's a technique called integration by parts. A quick recap. If you think about what techniques we have for finding integrals, don't we have the power rule, which is pretty good, right? It allows us to do x cubed And with a little bit of work, can't we use the power rule for square root of x and 5 over x cubed and things like that as well? We have a big bunch of ones that we just know the answer to, right? We know that the antiderivative of e to the x is e to the x, and that cosine x gets you sine x, right? We have a bunch of them. If you introduce the linear shortcut method, can't we do e to the 2x and sine of 4x as well? So we're getting that as our second major group of things that we are pretty comfortable about integrating. And then we had u-subs. Wasn't the u-sub technique really useful when things got messy and ugly? It allowed us to integrate some really ugly things. In my opinion, u-sub's very important technique, right? It's very useful. This guy is necessary, but he's not as useful as u-subs. In other words, if you randomly just went to a textbook and picked an integration, you're more likely to do a u-sub on it than you are to do this. But they are necessary because u-subs don't work in every other situation. So here's an example of when you would need to use it. If I asked you to find that guy, you cannot use a u-sub. Would you agree? There isn't even an obvious u-sub. No, trust me, you could try any u-sub in the world. It ain't going anywhere. Now, on the other hand, see if this was e to the power of x squared, couldn't you do a u-sub? Right, so it is possible to do ones that look like that, but not that one. So integration by parts is essentially designed for questions that look like this. Products, where the integral is made up of two things multiplied together, right? That's your most common situation where you're going to do integration by parts. You also are going to use it in situations where there's only one function. So you're going to use integration by parts, probably tomorrow, to find integrals for things like log x. And you might think, oh, I know the answer to that. It's 1 over x. Hold on a minute. Isn't the derivative of log 1 over x? Not the integral of log. You see where I'm going with this? So that is not possible right now, right? You do not know the answer to the integral of log x, would you agree? And you don't know the integral to this guy either. And put in a few more. You don't know how to get the integral of that guy. Agreed? So how does this work? It's a kind of combination of two things. It's a formula and a process. See, a formula is you just plug things in the places that the formula tell you to plug them in, and you got your answer, right? Like a plug and chuck. That's a formula you need. And a process is more like, isn't u-sub a process? You couldn't really call a u-sub a formula. I mean, I don't think there is any formula that would make sense for a u-sub. And it's a kind of bit of both. So here it is. If you want to find the integral of f of x, gx, dx, right? The integral of a product. It's f of x, capital G of x, take away the integral of f dashed of x, capital G of x, dx. Where f dashed x is pretty obvious what it is. It's the derivative of f of x. And we have seen this notation before. What does capital G of x mean?
Isn't it the antiderivative?
Yes. Right now, would you agree that's a formula? Right? It's a plug and chug where you put things in. And it is. That's the formula side of it. But it's also a process. So let me do this guy and show you the process. First thing you do, step one, is you identify who f of x is going to be and who g of x is going to be. And you might think, well, isn't this, isn't this going to be the f and isn't this going to be the g? Just like in the product rule, right? Differentiation in the product rule. Isn't the first guy f and the second guy is g? When you do the product rule, it doesn't matter who you call f or g, it works both ways. When you do integration by parts, the identifying of the f and g is important. Very often it's the first guy is f and the second guy is g, but it's not all the time, right? There are circumstances where it's the other way around. Now, if you pick the wrong one to be f and the wrong one to be g, you will find out later on that you've screwed up and it ain't working, right? And since there's only two choices, can't you just throw that one away and do it the other way around? But there are kind of rules that you can use to choose who to pick for f. I always think of who to pick for f because the other guy's g. Pick f as any polynomial, right? So x squared, x cubed, 5x plus 1, 2x on its own, anything with x's, pick that one as the f. 90% of the time, you'll be fine. That's the right guy you pick. And there are exceptions, but we'll worry about them later. So, in this question then, f of x is x, and g of x is e to the x. That makes the derivative 1 and the antiderivative e to the x. Step 2. Use the formula. So it should be f of x, capital G of x, take away the integral of f dashed of x, capital G of x, dx. So it's going to be x, antiderivative, which just happens to be e to the x, take away the derivative, which is 1, times e to the x, dx. So we are now looking at that line. Have you noticed that the original integral has now turned into an expression that involves a much simpler integral? In fact, isn't this guy doable? Can't we just write the answer to him down? And step 3 is continue the process until you get the answer. So x e to the x, if you integrate this, you get that guy plus a c. There's your answer. That's probably the simplest integration by parts question I could have thought of. It's really got 3 processes. Choose your f and g. Use the formula. And then continue until you're finished. So how about this one? The integral of 3x squared, the sine of x, dx. Just a little bit harder. Okay, who's going to be f of x in this question? It's not meant to be a trick one, should be pretty straightforward. Who's going to be the f of x in this question?
3x squared.
You all agree that it's what you see is what you got, right? Now you differentiate this guy, you get 6x. If you differentiate this guy, you get cosine x. So far, so good. That's step one done then. Let's use the formula. It's going to be f of x, capital G of x, take away the integral of f dashed of x, capital G of x, dx. So it's going to be 3x squared times the cosine of x minus the derivative times the cosine of x dx. And that's step two done. Uh-oh. Look at that integral. How do you think we're going to find that integral?
Do we have to do the same thing again, but with 6x being like our second set of f of x?
Yep. But you've done that before. Can you remember doing L'Hopital's rule? Didn't you have to do L'Hopital's rule sometimes 2 or 3 times before you're finished? Isn't L'Hopital's rule more of a process, really, than just a formula, right? So what you do, and that's why step 3 here is, continue the process until you've got an answer. So I don't know what the answer to this is yet. So this guy's going to be my F, and this guy's going to be my G, and just because I can.
Professor, sorry to interrupt.
No, go for it.
Commented and said, isn't it negative cosine? Because the antiderivative of sine.
Oh, well caught. Well caught. It is. Well caught. Now, since this is going to be a negative, can't we bring out here and make that a plus? You okay with me doing that in 2? This is negative, but I brought it out here with this negative to make it a plus. Well caught. I'm always saying that. You should have caps on. Differentiation cap, integration cap, right? Turn it to the side of something. Because in this process, don't you end up doing both things at once? Some things get differentiated, some things get integrated. And I've just did the classic mistake, haven't I? Where I integrated it, but I forgot and I differentiated it because it looks the same except for sign. So well caught, whoever did that. So this guy is now going to be 6x and his derivative is 6. And this time, I think I'm going to get away with it. That fella is going to be, and this time it is positive, isn't it? Positive sin x. So we've got 3x squared cosine x's plus an f dashed x, capital G of x, take away the integral of an f dashed x, capital G of x, dx. And I'm probably putting in more lines than you need, but these are kind of templates for doing the question. So it's 6 times sine x, take away nobody caught it. That's an f. So it's f of x G of x. So it's 6x sine x. Take away the derivative, which is 6 times sine x. Got that guy again? 6x sine x. Okay, we can integrate 6 sine x. That will get me negative 6 cosine x's. That's another negative plus 6 cosine x's. I'd see. Are we a little bit more comfortable with this process being repeated? That sometimes you have to do it. You can even predict how many times you're likely to do it. I'm not going to do it because it'd take me too long, but if that was 3x cubed, wouldn't I have to repeat it 3 times? If it was just 3x, wouldn't you just do it like once? 3x squared, you kind of do the process twice. If it was 3x to the 10, I ain't doing it. But if it was 3x to the 10, wouldn't I have to do the process 10 times to get the answer? So it's a good method, but would you agree it's got practical limitations? I mean, you can only really use it in relatively simple versions of it, right? X cubes maybe the top end. I wouldn't want to do anything more than an X cubed. Any questions about, oh, that's step 3 there. Any questions about that? No.
For the 6x sine x, is that not 6x cosine x? Do you not carry it down and then add the extra from 2?
Oh. So where do you think I've screwed up?
The 6x sine x,
Yeah.
the middle part. No, the part before that.
Yeah.
Yeah.
So it's f of x, which is 6x, times capital G, which is sine x, 6x sine x. That seems to be okay. F of x, capital G, f of x, capital G. I don't think that's wrong. Are we good?
Yeah.
Okay. But I mean, there are lots of moving parts in this, isn't there, as you've already seen? So you have to be extra careful. Let's do another one. What one shall I do? Oh. Let's do that one. That's my f. There's my derivative, none too special. Here's my g. Oh, let's put a negative in, that'll make it even uglier. Now, if you want to integrate e to the negative 2x, I agree you do get e to the negative 2x. Do you also get a negative 1/2? Are you happy about the negative 1/2 thing? I'm doing the linear shortcut method. So so f of x, capital G of x, take away the integral of f dashed x, capital G of x, dx. There's our basic formula. So make sure I put the pieces in. X squared goes first. The integral guy goes next. Take away the derivative and the integral. And all I'm going to do in this next line is tidy things up a little bit. Now that's a negative and that's a negative, so this can be a plus. That 2 cancels out with that 1/2. And so I believe you're left with that. Does that look good? Based on my previous carelessness. Okay, so aren't we really just going to do an f and g again? So this time the f is going to be x and its derivative is 1. And the g is going to be e to the negative 2x. And yeah, we're getting that guy again, just like above. So it's going to be negative 1/2 x squared e to the negative 2x plus the integration by parts formula. So it's going to be that fella. Okay, where we got f, which is x, and g, big G is that guy. Take away the integral. F dashed is 1, big G is that guy, dx. Just tidy it up again. You got this guy. If you multiply them together, you get that guy. These two negatives make a plus, and you eventually have that guy. If you keep doing it often enough, won't you eventually get to a place where you know the answer? And don't we know the answer to this one integral right at the end? So it's going to be negative 1/2 this guy, negative 1/2 this guy, and this fella is going to be a negative, eventually 1/4. I don't think I've screwed up. But if anybody sees something, it's possible. We look good. Right. When you do enough of these, you start seeing a pattern. And if you don't see the pattern, it's a kind of signal that you should be worried. Have you noticed that it starts with so many x squared, so many x's, and then there aren't any more x's? Do you see that pattern? That's pretty standard in these questions. So if this was x cubed cosine 4x, right, something like that, there'd be some x cubes with a trig function, some x squareds with a trig function, some x's with a trig function, and then just a trig function plus c. And if any one of those pieces was missing, then I would be worried that somehow or other I screwed up. So far, so good, right? Now, next thing is a side issue, but it's going to be important. When I do the integration by parts, the way I teach it is by this formula, as you know. There is another method called the UDV method. And I don't teach it. Some people like it, actually. I know some professors that teach integration by parts by using the UDV method. Go look it up. If you like it, use it. I have no problems with it. It gets you the exact same answer. You might want to say, well, can't we just see both methods? I typically avoid showing you two methods to do something. And the reason I don't do that, do you know what kind of happens? Is that people don't remember either method. They remember a bit from both, and they mix them together and make a Frankenstein method that doesn't work any of the times. So it's just simpler if I just stick to this method. Now, if you like it, great, you'll use it with me. If you don't like it and you look this up and you say, nah, this works for my brain, this method here, the UDV method, I'm cool with it, I like it, then use it. It's going to give you exactly the same working, right? It's going to look like this. It's just how you see it, right? How you visualize it, I guess. And I am getting really good at timing. It's 11:50, so your last name, and I'll see you tomorrow. I'll hang about for a few minutes if there's questions. We learned some cool stuff today. We now have a new technique for integrating. Okay, it's quite limited situations, but it does its job, called integration by parts. Okay, bye-bye, guys. As I say, I'll hang about for anyone who has a question.